Hello everyone, how you guys doing this morning? Pretty good, a little stressed I see. The end of the school year does that to anyone. Speaking of the end of the school year, it's kind of a good segue into announcements. There are two deadlines coming up for you here. May 20th, and I know you guys are sick of it because you're probably hearing it in all your classes, but May 20th, if I can get my computer to function here. That would be very distracting, Rebecca. So, May 20th is that last day to get any assignments or unit tests handed in. That's not the final exam. We are actually entering the last unit today. We're going to start that, even though you may not see it on the calendar till like Friday or next week. Even we won't have a live class on Tuesday because I have a doctor's appointment in the morning, so I'm not able to hold a live class, which is kind of why we're starting it today. But it's kind of a short unit. There's only 3 lessons. So really we have 3 lessons left to cover for the school year. And we have a month to do that in. Well, less than a month because May 20th is less than a month away already. But that kind of gives you a time span of what we're going to be covering in the next couple weeks here. Now, the lessons, even though we only have 3 lessons left, they're lengthy, okay, because they are calculus topics. So we're going to take our time through them, make sure we really understand them, and we're probably going to spend several days on some of those lessons in our live classes. So just a heads up with that. The other deadline besides May 20th is May 25th, and that is the last day at 4 p.m. to turn in your final exams. Juniors who took the ACTs this year, you did qualify to earn a final exam exemption pass. You'll be notified, I would say probably middle of May, so the beginning of this week right here. I think that's May 14th. You'll be notified if you qualify for that first choice on your exam pass. So I know a couple people in here chose math as their final exam pass, so you may not even have to take the final, which means May 20th you'll basically be wrapped up with pre-calculus for the school year then. So that's kind of exciting. Are there any questions regarding the deadlines at all? Yeah, yep. So that would be the 9.05 one, is what you're referring to? Yep, sure thing. So let me just bring up this 9.05 assignment. Remember 9.05 was talking about our mathematical induction? And I know there were a couple other questions that other people had as well with this number 2, so we'll go ahead and take a look at that one for sure. Okay, so I think what maybe happened was step 3, when we tried to set it up using k plus 1, maybe we didn't necessarily set up the left-hand side correctly. So I think that's probably where the mistake is coming into play here. Now, with the mathematical induction, there's 3 steps, right? Does it work for step 1 with the anchor? So when you substitute in, did it work? Okay, so that one came out true, so I won't really spend much time on that. Step 2 is then assume it's true for k. I'm not going to rewrite all of that. because all you're doing is just putting k in instead of n. So step 3 is where it's going to really hit the meat and potatoes, so to speak, of your induction here. So we're going to keep everything kind of the same. Dot, dot, dot. And then all of a sudden we run into that 3k minus 2 squared. And now we've got to add on the k plus 1. So the k plus 1 goes in for the n. So now we'll have a 3, and then we'll have a k plus 1 minus 2, and all of that will be squared. So that's what we're going to get on the left-hand side. Now all of this can be substituted for here, right? So you're going to have a k times 6k squared minus 3n minus 1 all over 2 plus this 3k, oopsie, yes, that should be a k, my bad. I'm going to make that into a fancy k then, or a weird looking k. 3k, I'm going to substitute this 3, or not substitute, distribute that 3 and then combine like terms. So that'll be a 3 minus 2, which is a 1. The right-hand side, we're going to get a k plus 1 times 6k plus 1 squared minus 3 times k plus 1 minus 1 all over 2. Now I'm just going to go ahead and multiply this by 2 as well so that they all have a denominator of 2. If they all have a denominator of 2, that can actually drop out of your problem then. So I'm just going to get rid, since I wrote the times 2 up here, I can get rid of all that division then. There's still a lot here to simplify, but at least getting rid of that division makes things a little less overwhelming. Okay, so do you want me to keep continuing from here with the simplification, or does this kind of help? Do you guys think you would be good from here with the simplifying? Let me know if you want me to keep going, or do you think you can handle it from this point with the distributing and then combining like terms? Simplifying is where you had the problems. All right, so the first thing I'm going to do is distribute the k. So a 6k cubed minus 3k squared minus k. Now before I distribute the 2, I've got to actually multiply 3k plus 1 times 3k plus 1. So off to the side or on a separate piece of paper, you need to do that multiplication. Thank you, Rachel. I was like, okay, what's that going to be? So to save me some time, Rachel's got it for me, a 9k squared plus 6k plus 2. Now I'm also going to go ahead and now I'm going to distribute the 2 through that, because I will go ahead and multiply everything by 2, and I see Rachel typing, so she's probably going to have that for me as well. Thank you. Now go ahead and, now that we have no parentheses left on this left-hand side, let's go ahead and combine like terms. So when we combine like terms, what do we actually end up with? So we definitely have a 6k cubed, but what else do we got here? A 15k squared, does that look right? 11k plus 2? Is that what you got yours to simplify to, Rachel? Does that look right? Okay, good. Now that the left-hand side is kind of done, we got to focus on the right-hand side. I would probably start with this k plus 1 squared and see what that is going to multiply to. So that will be your k squared plus 2k plus 1. And we have to also distribute a 6 through there. So that will be a 6k squared plus 12k plus 6. All right, I'm going to kind of line things up now with the rest of what's in here because I have to distribute a negative 3 next. So a negative 3k minus 3, and I have a minus 1. So inside this whole second parentheses here, we're going to get a 6k squared plus a 9k. 6 minus 4 is a 2 at the end, it looks like. The 2k came from k times 1 and 1 times k. So adding those like terms in the middle gives you a 2k. I'm going to go ahead and distribute the k plus 1 now. There's that 6k cubed, so fingers crossed we're kind of off on the right terms here. We're on the right foot. So when I finally combine my like terms, hopefully we get the same thing now that we had on the left-hand side. 9 plus 6 is our 15, k squared. Ooh, things are looking good. 9 plus 2 is our 11k. Woohoo! We got the exact same thing we had on the left-hand side now. Okay, usually, yeah, most of those stakes will happen when you are distributing or multiplying. So be careful of like those 3k plus 1 squareds. Make sure that you actually are multiplying 3k plus 1 times 3k plus 1. And then combining those like terms and then distributing through and then simplifying more. So this one was lengthy. There was a lot of simplification that needed to occur here. Any other questions with that mathematical induction at all? All right, on to our velocity. So we are going to start talking about kind of velocity to start us off with Unit 10 here. Unit 10 is actually Unit 11 in our textbook, so don't be confused by that change in numbers there. We're actually going to skip what's Unit 10 in the hardcover textbook and jump right into Unit 11 there. So if you're wondering why it switched there all of a sudden, is because we're actually going to skip what Unit 10 is in the hardcover textbook. All right, so we are looking at our calculus topics now that are going to appear in Unit 11 in the hardcover textbook now. So the first thing they talk about is average velocity. And average velocity is simply just the change in position divided by the change in time. So when we take a look at kind of a basic example here, it says an automobile travels 120 miles in 2.5 hours. What is the average velocity over that 2.5 hour time span? So they're basically asking for how fast are you going per hour. So what are we going to do to figure out how fast we're moving per hour? So if you're going 120 miles and 2.5 hours time, how do we figure out how fast we're moving on average in that time span? You're going to take your miles and divide by your hours. So 120 miles divided by 2.5 hours. How fast are you moving per hour? On average, you're going 48 miles per hour. That's what that average velocity is referring to there. So kind of a basic concept. You're just taking your distance divided by your time to figure out the average speed. Now that doesn't mean that you may not be going faster at times or slower at times. This is just the average speed that you're moving throughout that 2.5 hour time span. We're going to now compare that to instantaneous velocity. So instantaneous velocity is what's happening at an exact moment in time. So here Galileo experimented with gravity by rolling a ball down an inclined plane and recording its approximate velocity as a function of elapsed time. Here is what he might have asked himself when he began his experiment. A ball rolls a distance of 16 feet in 4 seconds. What is the instantaneous velocity of the ball at a moment of time, 3 seconds, after it starts to roll? So basically he's asking what's the speed at 3 seconds of this ball? So if we were to freeze it at 3 seconds, how fast is it moving? Well, if you're freezing it at a certain amount of time, it's not moving anywhere. Right? So this is what Galileo ran into. So you might want to visualize the ball being frozen at that moment and try to determine its velocity. Well, if the ball's not moving, it does not have a velocity, right? So that means it kind of sounds like a trick question, right? The average velocity, you could do 16 divided by 4 and get 4 feet per second. But when you think about the instantaneous velocity, it's going to be 0 feet over 0 seconds, and you can't divide by 0, right? So this is where he ran into some problems. So what he did is he said, well, let's try to make that change in time as small as possible. Since we can't divide by 0, let's make that as small as possible so that maybe we can try to approximate the instantaneous velocity. So here's kind of what he came up with. We'll come back to this one because technically we need some stuff before this. Notice that when we are going to be taking a look at instantaneous velocity, it's going to be referring to a limit, right? Because we can't find the exact value at that time, because at that time you would be dividing by 0. It's frozen. You can't do that. So if we get closer and closer and closer to it and get a number that's arbitrarily close, that is going to work as our instantaneous velocity. That is the exact same thing of what a limit is referring to, right? A limit is what your value is getting close to as it approaches a certain number. So we will be using limits here to find our instantaneous velocity. But here is what we're going to actually have to need or use. So on the bottom portion here, we're going to say that the limit as x goes to a, and a is going to be that certain time that we're looking for. So in Galileo's experiment there, I think they said it was like 3 seconds. What was that instantaneous velocity at 3 seconds? We're going to let our a be 3, because that's what we're trying to figure out at. What is that instantaneous velocity when it's 3 seconds? Okay. We can do that by taking f of x minus f of a all over x minus a. So they're going to have to give us a function to now compare this to as well. Now this value that we're getting here as x goes to a is going to be the slope of a tangent line to our original graph. So let's just say we have an original graph that's a parabola, something like that maybe. and we're picking that x value of 3. Essentially what we're looking for is what is a tangent line to that. So that value at 3 is going to be the slope of that line that kind of brushes up against it. Okay. Now, right above this box right here, it says we use limits to precede a definition for instantaneous rate of change. We also call that the derivative. You're going to hear this term used a lot in the calculus course. So if you plan on taking a calculus class next year or in college, you're going to hear that term derivative used a lot. There's a few ways to denote your derivative. So one way is using the little prime marking right here. So if you see like a y prime or f prime of something, that means you're taking the derivative of that. Another way they denote that might be dy dx. So if you see a dy dx, that is also denoting your derivative. So you want to use this process here that's boxed up to help you solve. Okay. We can use this derivative at a point if we are given an exact value as x approaches something, or we have another formula coming up shortly that allows us to find the derivative of our general function as well. So we can still find the derivative even if we're not looking at a certain point of our original function. So we'll have another formula coming up shortly, and it looks very similar to the one that I have boxed on the screen there. Okay, I am going to jump back a slide here now that we saw what was boxed on that for the limit there and our derivative at a point. We can use that to help us solve example 2. So it says a ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is exactly t squared feet. What is its instantaneous velocity after 3 seconds? All right, so we're looking for the limit as x goes to 3, right, of f of x minus f of a, and a in this case is our 3, all over x minus 3. So if I take this formula from over here, notice the f of x is still there, and I'm just replacing that a with a 3. Okay. Now f of x in this example is this formula of t squared, basically. And maybe I should use the exact same variables. So I'm going to change it up a little bit, and they're going to use t instead of x. So when I say f of x, that's just your t squared minus, now we have to find f of 3. So when I substitute 3 into this equation, what do we get? A 9. Yep. So I'm just going to put a minus 9 on top. And a t minus 3 would remain in the denominator there. Okay. Now if I substitute 3 in for t, I still get 0 in the bottom of my fraction. That's a problem because we can't divide by 0. So let's see if we can simplify this and use our algebraic magic to try to cancel some things out here. How might we try to simplify what this function is right here? Can't cancel out a t because that t in the denominator is attached to the minus 3. So we can't just cancel the t out because that has to be taken with the minus 3. Yeah, so now we have to factor the numerator. So if we try factoring the numerator, let's see if we can cancel a whole factor out. So t squared minus 9, what can that be factored to? Yep, that's your difference of squares. So that would be a t minus 3 and a t plus 3. I notice that they now both have a factor of t minus 3 that we can cancel out. There's nothing left to really do in order to simplify, so let's go ahead and substitute that value of 3 in for t. So what is going to be the instantaneous velocity after 3 seconds? Well, what is 3 plus 3? 6. Yeah, so we're going to say that the instantaneous velocity is going to be 6, and then whatever units of measurement they exactly had there. Feet, it looks like, feet per second. Okay, kind of weird, but we can apply those limit rules here to help us find that instantaneous velocity. Questions with that process at all? Again, the more we do, hopefully the easier this is going to become for us. But it's going to be a little bit rocky here at the start. This is why it takes a few days of looking at these in our live classes, I think, to really kind of understand them. So we're going to move pretty slow through this last unit here. All right, here's what we need to know to find the derivative of a function at a point. Some people think this is easier for computing, so looking at it as h goes to 0 of a plus h minus f of a all over h. So here's another format that we probably would want to add to our notes. This is what we call using the limits to find a derivative. So if you ever see something that says use the limits to find the derivative, this is essentially what we're going to be doing from here on out. We're going to be kind of following that setup right there that we just boxed. All right, so here we're saying find the limit of our function as f goes to 4, or f of 4 basically. So following our setup here, we're going to take the limit as h goes to 0, which is always a little bit worrisome, right? Because when I take a look at this setup, I have h in the denominator. Well, if I substitute in a 0 for h, that will always be a 0. So throughout this process, what essentially are we looking for to happen? So after I take care of this numerator, what exactly are we looking for to happen to be able to find the limit? We're looking for that denominator to cancel out. Yeah, so throughout this process, the denominator will always have to be canceled out with something in the numerator. If it doesn't, we made a mistake. All right, let's see exactly what we're trying to find in this numerator. So a in this case is our 4. All right, let's go ahead and see what we get here. So the limit as h goes to 0 of f of 4 plus h. Well, we're going to use this function here, and anywhere I see an x, I'm going to replace that with my 4 plus h. Okay, I have minus f of 4. So what is f of 4? If I come back to the start here and I substitute a 4 into this equation, what do we get as our output? Is that simplified to a 29? Anybody else get 29 there? Yep, I did too. Yep, Isaias did as well. Good. Okay, there's that h looming in the denominator. Fingers crossed that we're going to be able to cancel that out at some point. What we have to do from here is simplify that numerator. So let's start by taking this 4 plus h squared, and let's multiply that out off on the side somewhere. So I'm just going to come up here and do 4 plus h times 4 plus h. Go ahead, distribute that. What do you get when you distribute and combine like terms? All right, everybody agree there? Tommy put that in standard form for us as well, which is really nice of her. The next thing we're going to do is we're going to multiply through by a 2, right? Because that's where this 2 is now. So let's distribute a 2 through that, which looks like a 2h squared plus a 16h plus 32. I still got the minus 3 hanging around, and I still got the minus 29 hanging around. All right, combine like terms, and what are we left with here in the numerator? Just a 2h squared plus 16h. That's actually really good news that the constant drops out at the end, right? We want that constant to drop out at the end because now what can I do in that numerator to hopefully cancel out the h in the denominator? You can factor out that h. Very good. So if you factor out that h, you're left with a 2h plus 16. You have that h in the denominator. That will officially cancel out now. So the limit as h goes to 0 of 2h plus 16, you can now go ahead and substitute that 0 in for h. And what are you going to get for that derivative of f prime of 4? You're going to get just that 16 at the end. That's a lot of work for an answer of 16. Questions with how we did that though? So using this setup right here at the top, and then substituting that into the equation they gave us for f of x. Again, a little weird and unfamiliar territory here. It does feel like we're sleuthing. Once we do more of them, it hopefully will become a little bit more easier to understand. Fingers crossed. Now, you all are going to hate me because when you get to calculus, you're going to learn a shortcut for all of this. But it's really important to understand. I know. It's really important to understand this back work, though, with the limit process. Yeah, because I found out that when I taught AP Calculus, those who did a lot better with those concepts were the ones that understood the limit process and could do it this kind of long route here. But there is a shortcut way. I'm just not going to show you that quite yet. I'm going to keep that to myself for a little bit, make sure you guys get more comfortable with this limit process, and then I'll whip out the shortcut for you near the end of the unit. May have already told you. Ruining all the surprises here. All right, can we find the derivative of a function if we don't have a specific point? So that first example, we were finding the derivative at a point 4, right? When x equaled 4, what was that derivative value? And we should get a constant if we're looking at a certain point. But if we're not and we want to find the derivative of a function, we can still do that. The only thing that changes is instead of using a, which is a numerical value, a point value, we're just going to let that be an x instead. So let's go ahead and find the derivative of f of x equaling x squared. So we're just simply going to use this formula here and substitute that into this function of x squared. Okay, so I'm going to start the limit as h goes to 0 of f of x plus h. So this right here, we're going to go ahead and take our function, and anywhere there's an x, we're going to put in an x plus h. Okay. I'm going to subtract off now f of x. Well, f of x is just x squared. And I'm going to have that all over h. All right, I'm going to just pause there for a moment. Any questions on what we did by substituting these parentheses, so to speak, into our equation of x squared here? All right, let's go ahead and simplify. What is x plus h squared? So come up off to the side and actually distribute and combine your like terms for x plus h times x plus h. So I'm going to give you guys a few moments to do that while I write on the board here. Good. When I combine like terms in the numerator, what am I going to be left with then? Awesome. What do I want to happen at this point? So now that we're here, what would come next? You factor out the h from the denominator, because we are hoping that we can cancel that h out at this point. Okay, looks like we can, right? All right, one step that's left. What's my last step? Now that you're not dividing by 0 anymore, what can we do here? Now you can substitute that 0 in for h and see what you're left with. Yep. So it looks like we'd be left with just a 2x. Phew. Any questions with how we got 2x for that derivative? Again, notice this was the derivative of the function with respect to x. So we won't end up necessarily with just a constant there. I mean, sometimes you can, that's still a possibility. But sometimes when you are taking the derivative of a function, you'll have that variable left in that answer still. Okay, let's go ahead and do one more example here. Depending on how long this one takes, this might be the last one we can squeeze in for the day. All right, we want to find the derivative, and notice that they're using a different notation here. So that is still the derivative of the function y equals 1 over x. So we still want to use this setup up here, and we're going to substitute in this x plus h into this function of 1 over x now. Okay, so that's going to start off as the limit as h goes to 0 of 1 over x plus h minus 1 over x all divided by h. What am I going to do to kind of simplify things here? Because I can't just substitute 0 in for h at this point, because I'd be dividing by 0 still. So I've got to try to simplify what I've got written here. How do I simplify that? I'm going to focus on this numerator. Let's try to actually subtract these fractions. What do we need if we're going to subtract fractions? You need a common denominator. So this x plus h cannot be separated, by the way. What am I going to multiply this first fraction by so that I can work on getting a common denominator? Yeah, we have to multiply by an x. What are we going to multiply the second fraction by? An x plus h. All right, let's see what that leaves us with then. An x minus x minus h all over x times x plus h, all divided by an h still. Well, that x minus x, at least that's going to cancel each other out. So let's see what we're left with after we cancel those out. Looks like we have a negative h over x times x plus h. Now, I don't want to divide my fraction, so let's change this to a multiplication. But when I change that to a multiplication, we have to take the reciprocal of that denominator, right? So instead of dividing those two fractions out, let's change that to a multiplication problem. When you change that to a multiplication problem, what happens? What can we do at this point? You can cancel out the h. Yep. So if you cancel out the h, let's see what we have left. We have just a negative 1 in the numerator and an x times x plus h in the denominator. At this point, since there's nothing else to kind of simplify, let's go ahead and substitute 0 in for h and see what happens. When we substitute a 0 in for h, what does that simplify to? Obviously, we get a negative 1 in the numerator. Then what are we left with in the denominator? An x squared. Yep. So this is going to be the derivative of that 1 over x. Phew. That was kind of a lengthy process there. And again, what's going to trip us up if we do run into any issues is probably the simplifying piece of it all. So remembering all the different methods we've learned throughout the years on how to simplify these fractions. Any questions with anything? It is a tedious process, so finding the derivatives using limits is a tedious process. Okay, we're going to kind of wrap up there. I think with the time remaining, this is a good place to kind of stop. You do have enough information, though, to try out the 10.1 assignment. So give that a go over the weekend or early next week sometime. And in Thursday's class, we'll go ahead and start off by kind of where we left off with this 10.1 lesson, and then we'll venture into 10.2 as well. All right, remember, no live class next week, Tuesday, because I'm at a doctor's appointment. If you have questions with anything, don't hesitate to send me an email. What's really important, though, for the rest of this week is just making sure that you're comfortable with the Unit 9 material, because you do have that test coming up at the end of this week. So make sure that you're completing that test, and then you can look at 10.1 early next week or so. All right, that's all I got for you guys. Have a great rest of your week, and I'll see you all next week, Thursday again. All right, bye, everyone.